Okay, so this is our review session outline for the final exam. So I'll talk briefly at the beginning about the final exam in general, and then we'll launch into a review of the different chapters that we covered and some of the key topics in those chapters. It's necessarily going to be brief, but of course you'll have opportunities to ask me questions on Zoom later this afternoon, as well as during my office hours. So the final exam will have 70 multiple choice questions, and the time limit will be approximately 2 hours. Usually it's plus or minus 10 minutes or so on that time limit, but pretty close to a 2-hour time limit. Comprehensive, covering 351 and 352M. But because we have used many of the topics throughout the semester, and in this last section of the class, we've reviewed some of the topics we learned earlier, then it is not as daunting as it sounds to have a final exam covering an entire year's class. So you should bring your molecular models. You will be able to use those, but that and your pencil in your homework is really all you need to bring. We'll provide you with the scratch paper and so forth. Make sure you pace yourself, skip problems that look like they might take you a long time to solve. And then if you encounter any problems that look unfamiliar to you, if they're reactions we didn't explicitly cover in class, then just try to recall which reaction it most closely resembles, and that's usually going to help you solve that kind of problem. You've learned enough organic chemistry that you should be able to see a reaction related to one that we've learned in class and predict the outcome. So for studying for the exam, I would suggest going back and looking at your old exams, reworking those problems if necessary, reviewing them. Anything that looks unfamiliar to you, make a list of those topics, and then go back and review those topics. And as you view this review session, also any topics that I discuss that are unfamiliar, you'll want to make a list of those and go back and review those topics. Our textbook has a really good really good key concepts sections at the end of each chapter. Those chapter summaries are very well done. And so that's a really good place to go for the topics that you need to review. And then if you still have unanswered questions after reviewing via the key concepts sections, then you can go back to actual sections in the chapter to review things. Your homework problems also good practice, good help. So if you have not finished those, you're welcome to keep working on them up until the exam. If you've completed the homework and you're looking for extra practice, we only assigned you about half of the problems, so you can go back and work some of the unassigned problems for additional practice. And then, of course, there is the ACS study guide that provides lots of practice problems. I still have some in my office that students can check out if you so desire. So, and then finally, the Bacon quizzes. Those are also available as a way to help review for the final if you haven't done those already. Okay, and with that, then let's go into a review of the individual chapters that we covered, starting with Chapter 1. Chapter 1 was entitled Structure and Bonding. So this was primarily review from general chemistry, but there were some, we did emphasize resonance a lot here. So our key topics would be Lewis structures, resonance, a topic that certainly is familiar to you by now. And then we had our bonding theories, atomic orbital, molecular orbital, hybridization is a subset of atomic orbital theory. And then we had concepts such as electronegativity and polarity. So since these were topics that were introduced in general chemistry, and we've used all of these topics throughout the semester, then hopefully you don't have to go back and review too much in Chapter 1. So next, Chapter 2 was acids and bases. Another topic covered in general chemistry, but the way we focus on it in organic chemistry is different, namely comparing two or more acids and determining relative acid strength. So the key thing here is the four factors that we learned for determining relative acid strength, or the four effects. We have the element effects, we have the inductive effects, we have the resonance effects, and then we have the hybridization effects. And we have returned to this topic over and over again throughout the semester, comparing relative acid strength, comparing relative base strength. So hopefully this is something you're familiar with. Another key topic in this chapter that I'm not writing up here, but just the different definitions of acids and bases, the Bronsted-Lowry definition, defined in terms of protons, proton donor, proton acceptor, and then the Lewis acid-base definition, Lewis acids being electron pair acceptors, Lewis bases being electron pair donors. Okay, so Chapter 2, again, one that we should be pretty familiar with. Chapter 3 had kind of a very wide open title, very broad title, Introduction to Organic Molecules and Functional Groups. So that could mean just about anything, but as you know, we use this section to introduce what the book refers to as intermolecular forces. We often called them non-covalent forces because sometimes they occur in an intramolecular sense. But of course, we talked about van der Waals forces, dipole-dipole forces, and then our hydrogen bonds. And then we gave examples of the impact of these intermolecular forces on physical properties. I should also mention we talked about ion dipole forces in this section. Sometimes the book and other places erroneously refer to those as hydrogen bonds, but being able to distinguish them is important. So recognizing the different types of intermolecular forces or non-covalent forces, understanding their role in determining physical properties such as solubility, melting and boiling points. Those are the key things for this section. Again, these are topics and concepts that we have referred to throughout the year. So then Chapter 4, we started our first chapter on a specific class of organic compound. We talked about alkanes in this chapter. We use that as a way to introduce nomenclature. As you know by now, nomenclature is not my favorite topic, and we typically are testing nomenclature in an indirect fashion at this point in the class, where you're seeing the names of organic compounds in the problems, either in the questions or in the answers to the questions, and you have to know what those structures are to be able to answer those questions. And you'll probably see a few questions like that on the final. You'll probably also see a handful of straight nomenclature questions where they either would draw you a structure and you have to choose the correct name, or they would give you a name and 4 structures to choose from, and you'd have to choose the correct structure. So there typically are a handful of 100% nomenclature questions on the exam. They usually don't go into the minute details of nomenclature. So if you know nomenclature um, at the level that we have studied it in class, then you should be okay for any nomenclature questions that you encounter. And then the other main topic we had in this chapter was conformations. So this is where we started looking at the three-dimensional shapes of organic compounds. This is also something that we've continued to do throughout the year. And we started out with acyclic alkenes, looking at Newman projections, learning a lot of vocabulary such as staggered, eclipsed, gauche, anti, and then we looked at cyclic cycloalkanes, and of course, as you know, cyclohexane is our most important of the cyclic alkanes, and certainly understanding relative stabilities of chair conformations. That's a major topic, axial and equatorial, ring flipping, all that sort of thing. Okay, so then chapter 5, stereochemistry. Another topic that we have reviewed, we have used extensively. Hopefully the carbohydrate chapter provided you with a good review of stereochemistry. Amino acids, peptides, and proteins as well had some stereochemistry. So key things here, chirality, being able to determine if a molecule is chiral or not, stereocenters, being able to identify whether a given atom is a stereocenter or not, or counting the number of stereocenters in a molecule, determining R or S. Typically there's a problem or two where you have to determine R or S, so make sure that you are practiced at that, proficient at that. And then we have some of the more advanced topics on stereochemistry, diastereomers, meso compounds. So a lot of vocabulary in chapter 5. So make sure you understand all these terms and that you can apply them. And of course, as I mentioned, we have studied stereochemistry quite a bit throughout the year. Chapter 6, understanding organic reactions. That's another very open-ended title for a chapter. Understanding organic reactions can be a lifelong endeavor. I'm working on it myself and have been for decades. Sorry, understanding. Let's try this. But in this chapter, what we did was we learned some concepts. We reviewed some concepts from general chemistry and introduced some other concepts that can be used to analyze organic reactions and understand reaction mechanisms. So we talked about different ways of breaking bonds and making bonds. We talked about some thermodynamic parameters, enthalpy, entropy, free energy. We talked about, so one of the key things here in this chapter was the energy diagrams. We learned how to interpret energy diagrams. And so being able to interpret energy diagrams is an important skill. We had multiple choice questions on that topic earlier in the class. Then we talked about kinetics. And it is important to keep thermodynamics, properties related to relative energies of reactants and products, and kinetics, which is connected to the reaction rates. Very important to keep those distinct from each other. The concept of the transition state, how that plays into kinetics. So many of these topics in this chapter we employed in subsequent chapters as we were studying specific types of reactions. Okay, so the next two chapters, we'll put those together because they're both on alkyl halides. So chapter 7 was entitled Alkyl Halides and Nucleophilic Substitution. And then chapter 8, also entitled Alkyl Halides, but Elimination is the subtitle there. So in these chapters, there were 4 reaction mechanisms we learned. In chapter 7, we learned about SN2 and SN1. Sorry, the chalk is breaking. And then in chapter 8, we learned about E2 and E1. There were a couple of other interesting topics in these chapters, but let's take a look at our flow chart that we learned that enabled us to look at a given alkyl halide and a reagent, either a base or a nucleophile, and determine if that reaction, which of those 4 mechanisms that reaction would proceed by. So I won't go through this step by step the way that I did when we were covering it, but just a reminder, only alkyl halides undergo these reactions. Vinyl halides actually can undergo E2, but you won't see aryl halides undergo these reactions. So we need to determine whether they're calling it a nucleophile here, we'll just call it the reagent, whether that reagent is a strong base or a weak base. We used hydroxide as a dividing line there, and then we moved the line a little bit to say that DBU and DBN are also strong bases. And then strong nucleophile. We said that any negatively charged nucleophile would be a strong nucleophile. And then we said that ammonia, and in some cases, other amines would also be strong nucleophiles. So by determining which of the 4 categories your reagent fits into, weak base, strong nucleophile, strong base, weak nucleophile, strong base, strong nucleophile, or weak base, weak nucleophile. Determining which of these categories it fits into, and then being able to determine what kind of alkyl halide you have, methyl, primary, secondary, or tertiary, can allow you to predict the outcome of the reaction. And remember, in some cases, there are mixtures. We always get SN1 and E1 together. In certain circumstances, we can have mixtures of SN2 and E2. So this flow chart was from 351. We have posted it on the 352 Learning Suite. So if you go under Content, you'll see an entry that says 351 Mechanism Chart. So you can download this. And going through this chart, not memorizing it, but looking at it and making sure you understand the reason for the outcomes in each case is a sign that you have a good understanding of the concepts of substitution and elimination. All right, so we'll close that. Turn off the projector. Raise the screen and go back to the board. Okay. So there were a couple of other topics related to substitutions and eliminations that we had in this section. We learned about carbocations. Those are key intermediates in SN1 and E1 reactions. And then we learned the Hammond postulate in conjunction with that. helping us to explain why more substituted carbocations are formed faster. And then in the elimination chapter, we learned a little bit about stereochemistry in eliminations, the anti-periplanar geometry. We also learned Zaitsev's rule, explaining why the transalkenes are major products. It didn't have a rule associated with it, but why we would get more substitute. Actually, Zaitsev's is the more substituted alkene is the major product. We also learned that transalkenes are major over cis alkenes. Okay, let's see. I think maybe we'll erase the board now, and then we will continue with chapter 9. All right. Chapter 9, called Alcohols, Ethers, and Related Compounds. And those related compounds are epoxides, which are a type of ether, thioethers, thiols. All right, so we focused in this chapter on reactions of alcohols, which were substitution and elimination reactions, same types of reactions we learned in chapters 7 and 8, but we just learned a lot more examples of them in this chapter. So this chapter had a lot of different types of reactions. We had dehydrations, and then this was the chapter where we introduced carbocation rearrangements. So it's important. And we've seen carbocation rearrangements throughout the class. And so hopefully that's something you're used to looking for. When you can shift a group from a neighboring carbon to generate a more stable carbocation, that will happen faster than any intermolecular processes that could also happen to that particular carbocation. And then we talked about substitutions, converting alcohols into alkyl halides, the different ways to do that with HX or thionyl chloride or PBr3. We talked about how to prepare ethers. So we learned the Williamson ether synthesis, just a type of substitution. And then epoxide ring openings. The two types of epoxide ring openings with strong nucleophiles occurring at the less substituted carbon, with strong acids occurring at the more substituted carbon, both of those occurring with inversion. So the strong acid reactions are what we refer to as the SN1.5 reactions, the ones that have elements of SN1 and elements of SN2. Okay. And then, we had a little bit on thiols and sulfides. Those don't tend to feature too prominently on the final exam because those are kind of secondary topics. So I'm not going to say ignore them, but I would say focus on some of these other topics from chapter 9 a little more heavily than things like the thiols and the sulfides. So then our next chapter, chapter 10, was on alkenes. And the key thing, so with alkenes, we have some nomenclature, some physical properties, relative stabilities of alkenes. That was kind of the introductory material. Most of the chapter was focused on addition reactions. And some key things with addition reactions. We have an issue of regioselectivity when we're adding two different groups to an alkene. Which group goes to the more substituted carbon? Which group goes to the less substituted carbon? So that would be Markovnikov's rule. Some additions follow Markovnikov's rule, others do not. And then we had different mechanisms of addition that would explain stereochemistry. We have anti-addition. That's what happens when we're performing halogenations, for example, or hydrohalogenations. And then we have syn additions. That's what happens when we're performing a hydroboration. Then we have some reactions that give mixtures when we're adding HX, or when we're performing a hydration reaction, we get mixtures of syn and anti-products. So those are some of the key features of addition reactions. We also introduced a new intermediate in this section, the bridged halonium ion, those three-membered cyclic cations with a halogen. Okay. In chapter 11, alkynes. So this chapter paralleled alkenes because alkynes will also undergo addition reactions. So we had some addition reactions that were similar, comparable to the addition reactions we had in chapter 10. There was something new. We learned about tautomers here because when we hydrate or do a hydroboration oxidation of an alkyne, we generate an enol, and we learned that enols and ketones are tautomers of each other. And then we learned about acetylide ions. This was our introduction to multi-step synthesis, carbon-carbon bond forming reactions, deprotonating an alkyne with a strong base, such as sodium amide, NaNH2, and then using that acetylide ion in a carbon-carbon bond forming reaction. Okay, so those were our key topics in chapter 11. Chapter 12, oxidation and reduction. Again, a topic that you would learn in general chemistry, but we studied it a little bit differently in organic chemistry. And so here we learned about things like alkene and alkyne reduction. We use hydrogen and a metal catalyst such as palladium for many of these reactions. But then we have ways of reducing alkynes to get a cis-alkyne using the Lindlar catalyst, or get a cis-alkene, sorry, using the Lindlar catalyst. We can get a transalkene from a reduction using sodium and liquid ammonia. So understanding the ways of reducing alkenes and alkynes is important. And then we started talking about oxidations. We talked about dihydroxylation reactions. We talked about epoxidation. We talked about ozonolysis or oxidative cleavage. And remember, one skill related to this is sometimes they'll give you 2 or 3 different aldehydes or ketones, and they'll ask you what was the original alkene that was used to generate these products, and then you have to mentally glue those aldehydes and ketones back together to generate the structure of the product. So that's a sort of question that sometimes shows up on um, on standardized finals. And then we had oxidation of alcohols. So depending on the type of alcohol you have and the type of oxidant, you can get different results here. If we have primary alcohols and we oxidize them with PCC, we get aldehydes. If we oxidize them with chromium trioxide and acid, or dichromate and acid, we're going to get carboxylic acids. Secondary alcohols will give us ketones regardless of the method we use. And then, of course, tertiary alcohols cannot be oxidized. So understanding the different products you can get from alcohol oxidations and the types of oxidants in each case is important. So those were really the key things there. We did learn about the sharpless epoxidation. That was our first enantioselective reaction. I've never seen enantioselective chemistry appear on this final exam. If it does, I imagine it would be in the general sense, such as the way we discussed it in class. If you understand why you can obtain a major enantiomer and a minor enantiomer from a reaction, having those transition states be diastereomers, then you are pretty much good to go in that case. Okay, chapter 13, mass spectrometry and IR spectroscopy. So this was the start of our spectroscopy unit. We learned some theory behind the techniques, and that is, it is important. The questions do tend to be more weighted towards the interpretation, the application of these techniques to determine the structures of molecules. So not stressing too much about the theory, but just having a basic understanding, especially behind the theory or of the theory behind IR spectroscopy, since that's related to electromagnetic radiation in the spectrum. But being able to use these techniques to determine structures. We skipped over fragmentation because I told you that we don't use fragmentation patterns anymore to determine structures of organic molecules. NMR spectroscopy has allowed us to stop doing that. But sometimes fragmentation still sticks around on and does appear on standardized exams. If it does, all you need is a periodic table, which you'll have. We're taking the exam in a room with a giant periodic table. So all you need to do is be able to subtract your fragment from your molecular ion, and then that will tell you if a methyl group has been lost. So the difference would be 15, for example. If an ethyl group were lost, the difference would be 29, I believe. So common sense can usually help you solve fragmentation. So please don't spend time studying that. There are more valuable topics you can study, even though it could appear on the exam. But then for IR spectroscopy, the key things to memorize are 1700 being your CO stretch, and then 3000 being the dividing line between sp3 carbon-hydrogen stretching versus sp2 or sp carbon-hydrogen stretching. Those are just the key things. And of course, above 3000, we have OH and NH stretching, and those are very broad due to the hydrogen bonding. That's really what you would focus on for IR spectroscopy. Okay, so our next chapter, chapter 14, NMR spectroscopy. So this will definitely show up usually in terms of interpreting NMR data. They may give you NMR data and a choice of structures, and you have to choose the structure that matches the NMR data. or they could have other questions about splitting, about chemical shift. So really, we have our key, the important things in an NMR spectrum, the number of signals. Sometimes we give you a structure and ask you to tell us how many different signals would be present. So being able to determine if hydrogens are enantiotopic versus diastereotopic. The intensity of the signals or the integration, telling you how many hydrogens are present in each. The splitting of the signals, telling you how many neighbors there are, and then the location of the signals or the chemical shift, how that is related to the presence or absence of electronegative groups that are de-shielding those hydrogens, or perhaps electron donating groups that are shielding them. So NMR, hopefully, and if you've been taking the lab, you have an advantage here because Dr. Bronson gives you a lot of good spectroscopy practice when you take the lab. Okay, but definitely there will be some problems using mass spec IR and NMR spectroscopy to determine the structures of organic compounds. All right, let's go on to chapter 15. So chapter 15 was called Radical Reactions. And we started out this chapter with some basic information on radicals, their structure, relative stabilities, but the main thing here was the radical halogenation, of which there were two types, the chlorination reaction and the bromination reaction. And remember that chlorination is less selective, gives all possible products, whereas bromination is more selective, gives you the more substituted alkyl halide. And we explained why that was in the chapter. So that's important to review. And then a couple of other key reactions that we had in this section was the allylic bromination with N-bromosuccinimide. That's kind of related to the allylic oxidations that occur with unsaturated fatty acids, where oxygen can abstract a hydrogen atom and give you this allylic radical, which then reacts with another molecule of oxygen. But anyway, allylic radicals, the reaction you do in the lab would be allylic bromination. The reaction you don't want to have happen is the allylic oxidation of your unsaturated fatty acids. And then we had the radical addition to double bonds, addition of HBr to alkenes. And remember, we said that when you have peroxides present, you end up getting the less substituted halide, so it goes against Markovnikov's rule. Okay. Then we talked a little bit about polymers, but we can defer that since we've talked about them more extensively in chapter 31. So that's the end of 351. We'll erase the board again and start with chapter 16. Okay, chapter 16, conjugation, resonance, and dienes. So, well, I broke the chalk again. I'm going to run out of pieces of chalk. There's a bigger one over here. I'll be right back. Okay. Conjugation, resonance, and dienes. Okay. So the key topics are pretty much listed in the title of this chapter. We learned about how conjugation lowers the energy of molecules, how there are resonance structures you can draw when you have conjugation. And then we discussed reactions of dienes, and the key reactions of dienes that we learned about were addition of HX, and this is where we have 1,2 versus 1,4 addition, talking about kinetic products versus thermodynamic products, how sometimes we can have the less stable product being formed as the major product. That would be the kinetic product. And then we had the Diels-Alder reaction in this section. Okay? And we use the Diels-Alder reaction as a way to go in more depth in regards to molecular orbitals. And so those basic principles, this exam usually doesn't go in great depth into molecular orbitals, but those basic principles of molecular orbitals that we learned, that we reviewed in the context of the Diels-Alder reaction, are important to understand. And remember, we covered this on the videos that we used to cover for those first 3 class periods that we missed due to starting the semester late. So make sure you watch the videos for this chapter. Chapter 17, benzene and aromatic compounds. So again, this is a title that's very descriptive that covers many of the key topics here. So we learned about the concept of aromaticity, this extra stability that benzene and its derivatives have. We learned how to identify aromatic compounds, various types of aromatic compounds, including heterocycles, including benzene or benzene derivatives. Key thing here, being able to identify a molecule as being aromatic or not. Huckel's rule. Eric Huckel, this theoretical chemist who came up with this rule. Remember, there were 4 things that we had to have for a molecule to be aromatic: planar, cyclic, fully conjugated, and then 4n plus 2. I broke that piece of chalk. Pi electrons. So being able to identify aromatic compounds using Huckel's rule, that was a key feature of this particular chapter. And remembering heterocycles, a key thing with heterocycles is determining whether or not the lone pair on the nitrogen or the lone pairs on the oxygen, whether or not they are part of the aromatic system or not, because that impacts the properties such as the basicity. Okay, then chapter 18 was called reactions of aromatic compounds. So the main topic here was electrophilic aromatic substitution. And we had a general mechanism for this reaction, generating an electrophile, and then that electrophile being attacked by the benzene ring, giving us that resonance stabilized cation. And then there were, so in addition to knowing the reagents and the products in this case, we have our activating and deactivating effects of substituents on the benzene ring. Deactivating. And then we had our directing effects, ortho, meta, or para. So being able to understand those effects is important. And then we also had reactions on the substituents of benzene rings. We had ways of oxidizing alkyl groups attached to benzene rings, ways of brominating on the benzylic carbon. So understanding those reactions that occur on the substituents is also important. There was a topic that we skipped in this section, and that was nucleophilic aromatic substitution. Okay. In my opinion, it's a much less important topic than electrophilic aromatic substitution. It's much less common, so we focused on the more important topic. Occasionally, this does show up on the ACS final exam, but it's fairly straightforward. Again, it's one of those reactions. It follows kind of an addition-elimination mechanism, so it's kind of comparable to nucleophilic acyl substitution reactions. So if you see a question on nucleophilic aromatic substitution, probably you would be able to figure it out. But usually if it's there, there's only going to be maybe one question on that topic, so it's not something you should lose a lot of sleep over. Okay, chapter 19, carboxylic acids. And the acidity of the OH bond. And this was a review of acid-base principles designed to get us ready for studying carbonyl chemistry. We were comparing relative acid strength of different carboxylic acids, just went through some examples and reviewed those 4 factors or 4 effects that we learned back in chapter 2. So there's not a whole lot we're going to say about this particular chapter. We looked at benzoic acids as well. So we'll go ahead and jump into carbonyl chemistry. Chapter 20 was where we did that. Introduction to carbonyl chemistry. So this chapter had kind of a long title, Introduction to Carbonyl Chemistry, Organometallic Reagents, Oxidation, and Reduction. Okay? So a lot of the key topics in this chapter are covered in this title. Are organometallic reagents, Grignard reagents, organolithium reagents, organocuprate reagents. Remember, our Grignards and our organolithiums react essentially the same. And then the organocuprate reagents react a little bit differently. And then we had reductions. We talked about reducing carbonyl compounds, so that's a key topic. I'll actually go ahead and write that one a second time, even though it shows up in the title of the chapter, because we have our different reducing agents, sodium borohydride, lithium aluminum hydride, dibol or diisobutyl aluminum hydride, and how they will reduce species differently, with esters and acid chlorides, for example, sodium borohydride only reducing aldehydes and ketones. So understanding the reducing agents and their outcomes, understanding Grignard reagents and their reactions. Protecting groups was another key topic here. This is where we first introduced the concept of protecting groups with our TBDMS ethers that can protect alcohols. And then we first introduced something that we come back to at later times, in later chapters, alpha beta unsaturated carbonyl compounds, how they are electrophilic both at the carbonyl carbon and the beta carbon, and hence will react with organocuprates at the beta carbon. All right, so continuing on with carbonyl chemistry, chapter 21, aldehydes and ketones. And this is called nucleophilic addition. So, of course, the addition of Grignard reagents and organolithiums to aldehydes and ketones are nucleophilic additions, as are the reductions. So we've already covered that, but we covered, or introduced that, but we covered some different types of nucleophilic additions in this particular chapter. So we talked about making cyanohydrins. That's a topic we have returned to in the carbohydrate section of the class. And then we talked about the Wittig reaction. This is a unique reaction in terms of its mechanism. It's also interesting because if we have, for most alkenes, you've got two different combinations of a Wittig reagent and an aldehyde or a ketone that can be used to make them, and being able to identify which one is the best is an important skill in this case. And then we had imines and enamines. Knowing which of those is formed with which type of amine. We also learned about hydrates and acetals, closely related materials. Hydrates, of course, coming from reaction of water with our aldehydes and ketones. Acetals coming from a reaction of aldehydes and ketones with alcohols, and often used as protecting groups. Okay. Chapter 22, this was a large chapter. Chapter 22, carboxylic acids and derivatives, nucleophilic acyl substitution. So the key to this chapter is understanding the relative stability and reactivity of our carboxylic acid derivatives. And this exam tends to focus primarily on the organic ones and not the biological carboxylic acid derivatives. We stuck thioesters and acyl phosphates in there as the biological carboxylic acid derivatives. But this exam tends to focus more on, in my experience at least, the acid chlorides, the anhydrides, the esters, and the amides. Okay, so knowing the relative reactivities, the reasons for that, and then understanding the unique reactions of carboxylic acids. So our carboxylic acids differ from the derivatives because they have those acidic hydrogens as part of the OH, and we have to handle that. We have to take care of that in order to transform carboxylic acids. Okay. All right, so a lot of reactions in this chapter, but lots of similarities in mechanisms, lots of patterns that are followed, understanding which carboxylic acid derivatives we can produce from others, understanding that our amides are the most stable and they can only be converted into the carboxylic acids, which is helpful because we use them as the backbones of proteins and we don't just want them being cleaved. So with that, we'll erase the board and we're in the home stretch. We'll then go on to chapter 23. Okay, chapter 23, substitution reactions of carbonyl compounds at the alpha carbon. So this is where we learned about enols and enolates. Okay. So how they're formed, mechanism, their properties. We also learned about kinetic and thermodynamic enolates. We learned about an alpha halogenation reaction. The haliform reaction is kind of a subset of that reaction. And then we learned about malonic ester synthesis and acetoacetic ester synthesis. Now, of course, there's not going to be a short answer multi-step synthesis problem on this exam, and that's where we saw malonic ester and acetoacetic ester. But there definitely are ways to ask multiple choice synthesis problems, right? Giving you a list of 4 or 5 consecutive reaction conditions and asking you to predict the product, or perhaps giving you a starting material and a product, and then you have to choose the correct multi-step sequence to link that starting material to the product. So even though there's not going to be a short answer synthesis problem on this exam, I can almost promise you that you will see multi-step synthesis tested in a multiple choice format. So chapter 24 was kind of a continuation of chapter 23. This was our carbonyl condensation reactions chapter. And so in this chapter, we had a lot of name reactions. We had the aldol reaction, and there are lots of specific subtypes of aldol reactions that hopefully you can recognize and predict products. And then we had the Claisen reaction. There was a multiple choice question on exam 4 that class didn't do that well on, related to the beta oxidation of fatty acids. And I think maybe you were having trouble differentiating between aldol reactions and Claisen reactions, or retroaldol versus retroclaisen reactions. Remember that aldol reactions involve aldehydes and ketones, whereas Claisen reactions involve esters, and in the biological sense can also involve thioesters. And the same is true for the retroaldol and the retroclaisen. So distinguishing between aldol reactions and Claisen reactions is important. And then the other 2 named reactions we had here were the Michael reaction and the Robinson annulation. Okay, so understanding, being able to predict products. You're not going to have to draw mechanisms, but you've seen plenty of examples of multiple choice questions that test your understanding of mechanisms, and you can expect to see some of those types of questions on this exam. Okay, chapter 25 was on amines. Amines are unique among organic compounds in that they are the most basic of our neutral organic compounds. So we spent a lot of time in this chapter talking about the basicity of amines, comparing it, lots of different comparisons, alkylamine versus arylamine, pyridine versus pyrrole. So there were a whole bunch of comparisons that helped us review some of the concepts from chapter 2. And then a couple of other key reactions we had here. Hoffman elimination The Hoffman elimination goes against Zaitsev's rule, and we explained why that is. And then we discussed reactions of aryl diazonium ions. And then azo compounds were kind of a related topic to those diazonium ions because they can be formed from diazonium ions. And they're highly conjugated. Of course, that makes them very good as dyes. Then we went a little bit out of order. We went to chapter 29. Chapter 29 was carbon-carbon bond forming reactions. We started out with the organocuprates, the coupling of organocuprates and halides. Those can be alkyl, vinyl, or aryl halides, but the coupling of organocuprates with different types of halides to form carbon-carbon bonds. Then we went into some palladium chemistry. We had the Suzuki reaction. We had the Heck reaction. And as I mentioned, these are more modern topics, but they have made it into most organic chemistry textbooks now. And so they have started to show up on this final exam. So being able to predict the products, having a fairly basic understanding of the mechanism of those reactions would be important. And then we talked about carbenes as well as carbenoids. Carbenes are an important type of reactive intermediate. So understanding what they are, how to form them, and how they react. And then we concluded this chapter with the discussion of metathesis reactions involving the Grubbs catalyst. That's another modern topic that has started to make its way onto the exam, so you can't ignore that. All right, the last few chapters we won't say a whole lot about because they were on our recent exam, and so they should be very fresh in your minds, okay? So chapter 26, amino acids and proteins. Sometimes students wonder how the biomolecules are going to be tested on this exam. Generally speaking, in regards to amino acids and proteins, it's fairly, it focuses more on the amino acids, the acid-base properties of the amino acids, the isoelectric point, those sorts of things. Maybe a little bit on secondary structure, but more focused on the amino acids. Usually not terribly difficult. Chapter 27, carbohydrates. So carbohydrates, you're typically going to see things related to Fisher projections, Hayworth projections, trying to determine R or S from those sorts of things. So more focused on the structures and the stereochemistry of the carbohydrates, less likely to see things on disaccharides or polysaccharides or things like that. So having just had an exam here, you're probably well prepared. And then chapter 28, lipids. This is usually tested fairly superficially, having a basic understanding of steroids and the property of the steroid ring system being rigid, being able to recognize your types of lipids. That's usually good enough for this chapter. And then chapter 31, synthetic polymers. Usually the key skills with synthetic polymers are being able to look at a repeating unit and recognize the monomer or monomers that were used to construct that polymer. Sometimes they might ask things like, would you make this polymer by cationic polymerization or anionic polymerization or radical polymerization? That should be fairly straightforward. And then the other one would be being given a monomer or monomers being able to identify the repeating unit. That's typically what they would focus on with polymers. All right, so that's our review of topics. Enjoy your studying, and we hope to see you on Zoom later this afternoon.